Hello, young physicists. Ever wondered if particles like electrons could be secret wave dancers? Well, Louis de Broglie boldly proposed just that tiny particles, especially electrons, don't just behave like billiard balls but also like waves. He introduced the dazzling concept of matter waves, where the wavelength lambda equals Planck's constant h divided by momentum p. That's lambda equals h over p. Imagine electrons moving in circular orbits around a nucleus. Their wave nature means these waves must line up just right, like a perfectly choreographed dance, so the orbit's circumference equals an integer multiple of their wavelength. This means only specific orbits create constructive interference, a bit like musical notes that sound clear only when in harmony. These standing wave conditions naturally limit the possible angular momentum values to discrete steps, giving a beautiful wave-based explanation to Bohr's second postulate about quantized orbits. What's awesome here is that this wave picture bridges the classical idea of electrons moving in fixed paths and the strange quantum world where energy levels aren't just guesses but follow from wave mechanics. It's like discovering the secret rhythm behind the spectral light we see from hydrogen atoms, all thanks to matter waves. Now let's get a bit more mathematical, but don't worry, we'll keep it friendly. Imagine an electron with mass m zipping around a circle with radius r. Its momentum p, simply put, is mass times velocity v. That's p equals m times v. For it to behave like a standing wave on this circular orbit, the wave must fit perfectly all around. So the circumference to pi r equals an integer n times the wavelength lambda, or in words, to pi r equals n times lambda. Since de Broglie said lambda is h over p, we substitute to get to pi r equals n times h over p, rearranging, momentum p equals nh divided by 2 pi r. And since p is mv, plugging that in results in mass times velocity times radius equals nh over 2 pi. This product, mvr, is exactly the angular momentum L, and we have L equals n times h bar, where h bar is h over 2 pi. This means angular momentum isn't continuous but comes in neat multiples of reduced Planck's constant, perfectly confirming Bohr's quantization postulate but now with a wave flare. So it's not just a guess anymore, standing wave conditions make quantized orbits inevitable. Picture this, only orbits where the electron's wave beautifully fits like a bracelet around a wrist are allowed. This means the length around the orbit, 2 pi r, must be exactly equal to an integer number n of wavelengths lambda. We say 2 pi r equals n lambda, ensuring the wave does not cancel itself out but forms a stable standing wave. This natural matching condition sets which radii electrons can occupy, essentially quantizing the orbit size and their energy levels. Unlike Bohr, who assumed quantization, here these restrictions emerge naturally from the wave nature of matter. Imagine you're tuning a guitar string, only certain lengths produce a clear note, just like only certain electron orbits resonate properly. This wave interference inside the atom results in discrete energy levels, explaining the distinct spectral lines of hydrogen we observe. So the universe's music comes from waves in perfect harmony around the tiny nucleus. Let's link these lovely waves to the energy of electrons now. The de Broglie wavelength is given by lambda equals h over mv, where h is Planck's constant, m the electron's mass, and v its velocity. The total energy of the electron in an orbit can be expressed as negative ke squared over 2r, where k is Coulomb's constant, e is the electron's charge, and r is the orbit radius. Using the angular momentum quantization and the formula for radius r sub n equals n squared times h squared divided by 4 pi squared mek squared e squared, we derive the discrete energy levels E sub n equals negative me to the fourth k squared over 2 h squared n squared, quite a mouthful, but it matches precisely Bohr's energy formula. The beauty here is that energy quantization isn't an arbitrary rule but directly results from these wave boundary conditions restricting the electron's motion. It's like the electron's wave nature and the atomic dance floor create energy steps, not just at random but as a fundamental quantum design. Theory is wonderful, but how about some experimental punch? The famous Davison and Germer experiment gave the final applause to de Broglie's idea. When electrons were fired at a nickel crystal, they didn't just behave like tiny balls, they produced clear diffraction patterns, much like ripples in a pond. These patterns matched the predicted wavelengths given by lambda equals h over mv, directly confirming the wave nature of electrons. Seeing electrons create interference maxima and minima tells us they truly act like waves when accelerated through electric potentials. This was the first direct, experimental evidence that electrons are not just particles but also waves, backing up the whole quantization story with solid proof. So, the next time you think waves are just about water or sound, remember electrons can dance waves too. Let's wrap up. De Broglie's key formula is lambda equals Planck's constant h divided by momentum p, or more simply, lambda equals h over mv for electrons. The standing wave condition means to pi r equals n times lambda, leading us neatly to quantized angular momentum mvr equals n times h bar. This results in discrete energy levels E sub n equals negative me to the fourth k squared over 2h squared n squared, just as Bohr predicted. The big takeaway? Electrons behave like standing waves wrapped around the nucleus. Their angular momentum quantization isn't just an assumption, it's a natural outcome of wave constraints. De Broglie's relation beautifully explains Bohr's postulate, and the electron diffraction experiments put the cherry on top. Physics isn't just about particles bumping into each other, it's about waves shaping the very fabric of atomic life. That's all for today's concept. Remember, physics is fun when you laugh and learn. See you in the next session.